Alright, so we found our test statistic. Now for what we can do with that test statistic. So there are, let's see, three main types of hypotheses tests, and these will determine how we use the test statistic. So there's two-tailed hypothesis test, left-tailed, and right-tailed hypotheses test. So the tails in a distribution are extreme regions bounded by critical values. I'll explain more what each of those terms mean in a bit. And determinations of p-values and critical values are affected by whether a critical region is in two tails, the left tail, or the right tail. It therefore becomes important to correctly characterize a hypothesis test as two-tailed, left-tailed, or right-tailed. And those are kind of based on not equal to, less than, or greater than claims, which we'll see with some more illustrations here. So basically, in a two-tailed test, well, still always have some form of equality in the null hypothesis. So like with the XOR method, for example, p equals 0.5, then say we just wanted to say that the XOR method just was different, not necessarily that it's better or worse, just that it's different. We could use not equal to. And then this is what it means by two-tailed tests. These regions on both tails represent like where we would reject the H naught. Because again, these represent probabilities in these regions here. So if we ended up with a probability that landed in either of these areas or added up to, so sorry, at least we'll add up these probability regions, and if we get a probability that's less than those, then we'll reject H naught. Say we want to have a left tail test, again, null hypothesis having some form of equals. Alternative hypothesis then has a less than case for this one. And so we want to, if we end up with probability is less than over here, that's when we reject H naught. Otherwise, we all fail to reject H naught. And then finally, right-tailed test is when the alternative hypothesis should have some form of greater than in there. So that's like our XOR method, an example here, because we were saying p is greater than 0.5. So if we end up with probabilities in that region, that's when we'll reject H naught. And so now to finally specify a bit more, the p-value or probability value is the probability of getting a value of a test statistic that is at least as extreme as the one representing the sample data, assuming that the null hypothesis is true. So, like, for example, with the right-tailed test, the p-value is what we're going to get after we use the test statistic. And so if our p-value, so probability we get from the test statistic, if it falls in this region, that's when we reject H naught. And so the critical region in the left tail just means the p-value equals the area to the left of the test statistic, so less than. Critical region in the right tail, p-value equals the area to the right of the test statistic, so greater than probability. And then critical region in two tails, p-value equals twice the area and the tail beyond the test statistic. Or it could just be adding up the less than and greater than probabilities. So the null hypothesis is rejected if the p-value is very small, such as 0.05 or less. And again, this is all based on the rare event rule for hypothesis tests. Again, that is, if under a given assumption the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. So, like say for example, we find that our probability is very small, so like in these rejection regions, then we know there's nothing wrong with the probability, it's just the probability. If it's really small, that's when we then say that our assumption must not be correct. So that's why we're rejecting H naught kind of as that assumption. Sorry. Okay, then a little more specific example with that. So again, using this XOR method, same null hypothesis, same alternative hypothesis. We found that that test statistic was 1.6 again for that z-score. And now we can use that z-score to find the actual p-value, so that actual probability from the z-table in this case, since we used a z-score. And essentially, since this is a greater than hypothesis test, then my p-value is this area to the right of that test statistic of 1.60, which when we would look up that probability, it's 0.0548, which you can look up in a z-table. And I'm going to show you, just keep in mind, so this is to the right of 1.6, but z-tables only show us to the left probabilities. But if I were to look up something to the left of negative 1.6, that area would be the same as this area here. So I can look that up here, and these are the negative z-score values. So if I look up negative 1.60, then I see that probability is 0.0548. So the same value for the p-value. And so, let's see, just a little visual here for a procedure for finding p-values. And just based on, say, it's a left-tailed, then p-value equals the area to the left of that test statistic. If it's right-tailed, the p-value equals the area to the right of that test statistic. And keep in mind, you can use some of those same z-table features to your advantage, like I just did with changing that test statistic to the negative and looking for that left area, because it'll be the same. And as for two-taileds, then it'll just be equal to twice the area to the left or twice the area to the right, depending on where your test statistic is at. It's like if you were to put this tail region and this tail region together, those probabilities. It's kind of how you would find two-tailed probabilities. Now, just to specify a bit more here, the critical region or rejection region is the set of all values of the test statistic that cause us to reject the null hypothesis. For example, see the red shaded region in the previous figures. And so again, just if we end up with probabilities that correspond to those red regions, so just kind of like small extreme probabilities, and that's when we reject the null hypothesis each time. Then a critical value is any value that separates the critical region where we reject the null hypothesis from values of a test statistic that do not lead to rejection of the null hypothesis. So the critical values depend on the nature of the null hypothesis and the sampling distribution that applies in this significance level. Major importance on this significance level there is, again, if it, say you get a p-value below the significance level, that's when you reject the null hypothesis. So for example, again, using that XOR method scenario, then the critical value of this region with that alpha level 0.05, see, we're showing it below here. Notice this critical value is equals 1.645. Now, you can find your critical values based on the z-table also, in this case. Since we have that alpha of 0.05, that just means this probability of this area is 0.05. So I just need to find the z-score that separates that 0.05 there. And so I can find that in a z-table. I'm going to use that same trick where I'm going to look at this area on the negative side. I want to look for 0.05 as close as I can find here. I'll get a negative z-score. I just change it to positive, and that's my critical value. So I'm just going to look for 0.05, or as close as I can find to it on the z-table. So I'm looking inside in all these probabilities here. And if I trace over here, I find probabilities of 0.505 and 0.0495. So both of those are equally close to 0.05. And so when I would trace those back out, I'd see negative 1.64 is a z-score for a critical value, and negative 1.65. Either of those could be good critical values, but notice in your particular z-table, this one is starred because that's a common critical value of negative 1.645. Right, and then, let's see, just a little caution here, just trying to make sure you don't confuse the p-value with proportion. So just p-value is that probability of getting a test statistic at least as extreme as one representing the sample data. And then p is just going to stand for that population proportion. So they can both be kind of thought of as probabilities. Well, more so just p-value can be a probability. P is just the proportion. It's just the best distinction. Okay, so now back to step 7 for what we can say after we found either the p-value or critical values and where our test statistic lies relative to those. So we can make our decision to reject H0 or fail to reject H0. And the methodologies depend on if you're using the p-value method, critical value method, and then there's also a confidence interval method that you can use for hypotheses tests. So in the p-value method, it's all based on that significance level alpha. It's always if your p-value, that probability is less or equal to alpha, you reject H0. If your probability p-value is greater than alpha, then you fail to reject H0. So like in those pictures, if your p-value falls in those red regions, reject H0. If it fell in those green regions, fail to reject H0. So again, reject, fail to reject. Now with the critical value method, it's essentially the same idea, just not going as far to the actual p-value. So if the test statistic falls within the critical region, reject H0. If the test statistic does not fall within the critical region, fail to reject H0. So if we're using the critical values, we're basically just working with just the z-scores. We're just not finding the probabilities. So I know that's my critical value. If I found my test statistic value was less than that in this green region, then I fail to reject. If it was in this red region past the 1.645 in this case, then I'd reject H0. And then with the confidence interval method, you'll basically use your test statistic to create a confidence interval. Then if your claimed value is not in the confidence interval, you reject H0 because it doesn't fit in the claim. Then if the claim value is in the confidence interval, then you fail to reject H0. Just continue on with the example there. So same XORT method context here, same alternative and null hypotheses. Then, so using the p-value method, we would fail to reject the null at the 0.05 significance level, since we were getting that p-value of 0.0548, and 0.0548 is greater than 0.05, so that's why we failed to reject it. And then same thing would happen with the critical value method. Since we got our test statistic of 1.6, then the 1.6 is less than the critical value of 1.645. So in either case, we fail to reject an H0. Now our 8th and final step in the hypothesis test here is just to restate the decision using simple non-technical terms. Now, some of these terms may not be quite so simple and non-technical, but ultimately they're just non-statistical sounding terms that we're going to try and basically put our conclusion into context with the problem. So just stating a final conclusion that addresses the original claim with wording that can be understood by those without knowledge of statistical procedures. And so again, just kind of putting into context is important here. And for example, for the XORT method, for the XORT baby gender test, there was not sufficient evidence to support the claim that the XORT method is effective in increasing the probability that a baby girl will be born. So we didn't use any reject H0 or fail to reject H0 terminology in there. So that's kind of most of the reason why this one is considered the non-technical conclusion. All right, and then let's see, here's a little visual you can use for kind of helping decide what your final conclusion should sound like. I'm going to pick up in the last part of these videos here.